Our next speaker this morning is Julien Simon. Julien is AI and machine learning evangelist at AWS and for the whole of EMEA, Europe, Middle East. And Julien also is one of the few people in Europe who has this great t-shirt. No, I'm kidding.
Yeah.
Who has one of these DeepLens devices. Did I spoil it? No, yeah, it was in the title.
No, it's there. It's there.
It's right here. So really excited to see how that works, what's under the cover, what you can do with it. And yeah, let's welcome Julien on stage.
Thank you. So good morning, everybody. My name is Julien. I figured we would have enough geeky T-shirts, and you can't have any conference without a heavy metal T-shirt. So there. And we have way too many French people in the room today. What's going on? Why don't we do this in Paris then? Next edition? Yeah, no visa issues in Paris. Okay, so my talk will focus on trying to do machine learning and deep learning at the edge. At the edge means outside of data centers. So I'm going to talk about deep learning at the edge, which means running machine learning and deep learning prediction outside of the typical environments where you would run them. Literally anywhere, right? So I've got my camera here. Hopefully it's going to work. It won't have any technical issues today. We'll see. If I have technical issues, we'll figure them out. So what would we need to run deep learning at the edge? What would be the first maybe 3-4 things that we need to worry about in order to run this successfully? So probably the first thing we need is to be able to experiment in the cloud. Because obviously, even if we want to deploy at the edge on cameras and any kind of sensor, drones, etc., we still need to work with data sets in the cloud. And we need to train at scale. Okay? If we work with smaller data sets, we can work locally. We can work on some servers in the closet. That's fine. If we're talking about terabytes, maybe petabytes of images, video, sound, voice, etc., we tend to think, and our customers tend to think, they need scalable infrastructure, and the cloud will give them that. Of course, one of the challenges of running deep learning at the edge is that these devices tend to be very, very tiny, right? They have small CPUs. They have little memory. They don't have a lot of storage. So we can't take for granted the fact that whatever model we run in the cloud on powerful GPU servers is going to run just fine on a Raspberry Pi or on an Intel Atom CPU, just like the one in this camera. So we need to worry about performance, right? We don't want to wait 20 seconds to predict, say, a single image. And of course, the last thing that we need to worry about is deploying all that stuff. Okay, when you deploy to your servers or your cloud environments, you used CI/CD and Docker and all kind of different mechanisms to do that. And well, then guess what? They're not going to be available on embedded environments and on devices like this. So deploying, updating code and model are going to be a concern. So let's look at these 4 different things. So experimenting in the cloud. So as you probably know, AWS has been supporting the Apache MXNet project for a while now. It's our preferred deep learning library. We use it to build our own services, and we contribute to the project. And one of the reasons why we do that is because we feel it has the broadest selection of languages. If anybody in the room would like to use Perl to build deep learning models, raise your hand. Ah, you're ashamed, aren't you? Right. You should be, because probably you want to do Python, right? But if you wanted to do R, if you wanted to do C++ for maximum performance, Scala, etc., these are available. And we see this as an advantage over other libraries. And we can't expect all our customers to use a single language. Recently, this MXNet project introduced a new API called gluon. Initially, the MXNet programming model is a symbolic model. So you defined the network using symbols. You compile those symbols into a graph. You optimize the hell out of it, and then you train it and you predict. So that's great, gives the best performance. That's the way TensorFlow works as well, and others. But the problem is that your training process tends to become a black box. It's very difficult to inspect it, to stop it, to debug it, to change it, because it's been optimized and doesn't look like your initial model anymore. So the gluon API uses imperative programming, so you can actually define by run your model. You can use the Python debugger if you want to. You can stop the training process. You have full control over the training loop, et cetera, et cetera. So it's generally code, which is fine, and you can work with it just like you would work with any other piece of code. And another thing we like in MXNet is the extensive model zoo. Especially, there's a large collection of computer vision models, which are likely to be popular applications for edge devices. And they've been pre-trained. You can use them as is, or you can fine-tune them, obviously. And in this collection, which I believe is the biggest I've seen so far, you'll find some good models like MobileNet, SqueezeNet, DenseNet, etc. that work pretty well on resource-constrained devices. So what about training? So you could train on CPU-based instances like the C5 instances that we launched. You could train on the GPU instances, the P3 with the latest NVIDIA chips, the V100. And on those instances, you could build everything yourself. Just fire up some instances, use the deep learning EMI, which is the Amazon machine image that we provide pre-installed with, I don't want to say everything because we're always going to miss something, but I would say most of the open source and machine learning and deep learning tools that you need out there. Okay, so you just fire up your server, and within minutes you can get to work. But probably what you want to do if you need to train at scale is to use this new service that we launched at reInvent a few months ago called SageMaker. It just lets you focus on the machine learning task and basically frees you of any infrastructure task. Okay, so it doesn't matter if you need to train on 100 instances. It doesn't matter if you need to deploy on 100 instances. It's just one API call away. All infrastructure is fully managed, and you could just focus on improving the model, understanding the data, and do away with the plumbing. And we tend to see infrastructure as plumbing. Now, once you have a model, what about running that model at the edge? So what about speed, right? It's all about speed in the end, and accuracy, I guess. So MXNet is natively written in C++. So it's, I would say, as fast as possible. So even if you use the Python API or the Scala API, in the end, you end up calling highly optimized C++ code. So you don't waste too much performance by using those high-level languages. If you use gluon, you can hybridize the models. So you can actually compile your models into symbolic form, which will let MXNet optimize memory, optimize performance, and you get really, really close to native performance when you do that. So that's a thing that I see a lot of customers doing. They use gluon, the flexible part of gluon, for experimentation, and then when they have a working model and they just want to squeeze every possible bit of performance out of it, they just hybridize it, which is just one API call that compiles it into that optimized representation. And they don't have to rewrite anything, okay, which is a shame because, again, I used to see a lot of people maybe experimenting in Python and then having to rewrite everything in C++ using potentially different libraries, which is always a risk and time-consuming as well. So here, you don't have to do that. You can throw a couple of performance-oriented libraries into the mix, like MKL, the Intel library, that uses optimized implementations of math primitives, specific instruction sets, like the Intel AVX, just to speed up linear algebra, convolution, etc. There's also an open-source library called NNPack, which is similar, And it also works on ARM-based architectures, such as Raspberry Pis, which I love dearly. So I want to point that out. And one cool technique that you can also use in MXNet is called mixed precision training. And basically, you're going to use 16-bit weights and activations instead of 32 bits. And that gives you two benefits. The first one is obviously that the model will be twice smaller, which doesn't really matter when you deploy on big servers, but it does matter a lot when you have to download it to tinier devices over potentially unreliable networks. And of course, 16-bit arithmetic is going to be quite faster than 32-bit arithmetic. So you'll get a performance boost as well. So mixed precision training is a very cool technique, and there's hardly any loss of accuracy. So pretty interesting, even in the cloud space, I would say. So now what about deployment once we have a model? So ideally, I think this would go like this. So you would train a model in SageMaker. You could train at scale in the cloud using your favorite environment, TensorFlow, MXNet, scikit-learn, bring your own, do whatever you want there. You could bring your own model that you trained on your own servers as well, of course. You would write a Lambda function. Okay, I'm not sure if everybody's familiar with Lambda. Lambda is our function as a service that will launch, believe it or not, in 2014. And this lets you deploy tiny pieces of code into the cloud on fully managed infrastructure, without having to worry about scaling and anything else. So you would write that Lambda function, and what would it do? Well, it would just grab some data from your device and from, we'll see an example with the camera, maybe a video frame or something. And it would run it through your deep learning model and perform prediction, right? And maybe send back some results to the cloud or change the video feed, etc. You would add both the Lambda function that you wrote and the model that you trained as resources in a service called Greengrass. So Greengrass is an IoT service that we released a while ago that lets you deploy code in the form of Lambda functions, code to edge devices. Okay, and you'll see an example in a minute. So a Greengrass group is just at least one device, obviously. It could be a collection of devices. And you can attach code, a piece of code and a model to the group, and then Greengrass will do the deployment automatically. Okay, and that's what it will do. So on the device, like this one here, we have a small Greengrass SDK that connects to the cloud and gets code updates and model updates automatically. And it doesn't matter if you're deploying to one device or 1,000 devices, it's just going to work the same. So it really solves the deployment problem, which when you work with embedded systems is always a nightmare. So this is a good solution if you want to have the exact same programming model in the cloud and at the edge, right? You just want to write code that you can test in the cloud and then deploy seamlessly to your edge devices using the exact same code, exact same technology. If you need to update code and models often, okay, which is likely, I guess, then Greengrass is a good solution because it's going to handle deployment, it's going to handle retries, it's going to handle everything. So it's going to help you solve maybe the fact that network connectivity is not there all the time or unreliable, et cetera, et cetera. It's just going to do that for you. Okay. The requirements, obviously, is that the devices should be powerful enough. So I would say it's hard to give exact guidelines. I would say anything smaller than a Raspberry Pi might be challenging. Okay, if you have a smaller model, then you might be okay. But I would say anything much smaller than 1 gigahertz clock speed and 1 gigabyte of RAM, or maybe 512 megabytes of RAM, is going to be difficult. But it doesn't mean impossible. And of course, you need to provision the devices in AWS IoT. You need to create a certificate and a key pair for authentication, encryption, etc. Security is important. So just a few months ago, actually, we introduced a new revision to Greengrass. It's called Greengrass ML. It's still in preview, but you can join it. So the way this works is actually pretty simple. you have a Greengrass device with the Greengrass SDK installed. It's connected to the cloud every now and then. And whenever needed, the cloud is going to push a new model and a new Lambda function. Okay, so whenever you update the code in the cloud, it will get pushed to your devices. Same thing for the model. Okay, the difference here is that you can deploy them separately. Okay, previously you actually had to combine the code and the model, which I guess was inconvenient because every time you needed to change one single line of code, you had to deploy everything again. So if you had a 100 megabyte model, that's a big download just to change one line of code. So now you can actually manage those separately. The Greengrass framework on the device will fire up the Lambda function, and it's going to run some predictions. Okay, so it's going to loop forever and run some predictions using the model, everything happening locally, and then results, insights, predictions, however you want to call those, can be, they don't have to, but they can be sent back to the AWS cloud using IoT messages, why not? Okay, so this is Greengrass. So let's take a quick look. Okay, so this is yeah, I think it's large enough. This is the Greengrass Console here. So we see two groups. One of them is a Raspberry Pi sitting at home, and the other one is my camera sitting down there. Okay, so let's look maybe at this one first. So this group is just a single Raspberry Pi, and in this group, I attached a Lambda function. So this Lambda function is just grabbing frames from the Pi camera and running predictions. Okay, and I also defined resources. So I can actually define hardware resources. So I can give access to my Lambda function to, in this case, the camera and the memory of the camera on the Pi. So I can control that. If I had a GPU in there, maybe one day, I could give access to that GPU as well. Just make sure my resources are visible from the Lambda function. And then I can attach a model as well. Okay, so in this case, it's a SqueezeNet model. I could pick a model. So I could pick any model basically from S3, or of course I could go and select a model that has been trained on SageMaker to make that again transition from the training environment to the deployment environment super simple. So just grab a model here, and that would get deployed. Okay. So here we provide pre-built binaries for Raspberry Pis, Jetsons, NVIDIA Jetsons, and a third one that I keep forgetting about. Sorry about that. We provide pre-built binaries for MXNet, etc. But you could really bring any kind of library. If you wanted to use scikit-learn or TensorFlow, you could use the exact same mechanism. It's just that, of course, your Lambda function would have to use the scikit-learn APIs or the TensorFlow APIs to do that. Okay, and then you can deploy this as often as you want. And if I had let's say a code update, I would just click on redeploy or call an API, obviously, and this would just push the updated code and or the updated model to my fleet of devices. Okay, and if some of them are powered down or if some of them are unable to access the network, fine. We can try later. It's again, Greengrass is going to take care of that complexity. So, what about a real gadget here? So at reInvent, we also launched DeepLens. Come on, DeepLens. Yeah. Yep, here you are. So it's a camera. It's based on an Intel board. It has a tiny, I hate to call it GPU, let's say a graphical accelerator on that board. So it has nothing to, it's millions of light years away from, let's say, a big NVIDIA GPU, but it has a couple of hundred cores, which are good enough for our use case. So this is running Ubuntu, and And of course, it's pre-installed with Greengrass and everything we need to play with it. So how does it work? So basically, we're going to do pretty much what I showed you. We're going to we're going to register the camera to AWS. That will create a Greengrass group for the camera. And we can attach Lambda functions. We can attach models. We can deploy them automatically. And then, of course, we can apply those models to the video feed. OK? So you can take a closer look if you want later on. But I guess we should just plug it in and start playing, right? So here we go. All right. OK, so let's see if I can type my password now. Wow, OK. Amazing. OK, so as you can see, this is vanilla Ubuntu. And so I've got two HDMI connections here. One would give me the original video feed, and the other one will give me the feed that has been processed by the Lambda function. So I'm going to jump to that one directly. And this looks like the right thing. OK, so let's see if I can find more people here. All right. OK, so the model that is deployed here is an object detection model. So don't be offended, but you are objects to this camera. One of the objects that can be detected is actually people. OK, but the font is really, really tiny, but it's actually able to pick up chairs. So if anybody has a cat, a dog, or a sheep, you should be able to pick those out as well, but I guess not, right? Louis wouldn't allow them. So chairs, maybe bottles, and things like this. OK, but people work pretty well. OK, so let me put this down again. You can come and take a closer look later on. So how does this work? So again, when you register the camera, you can pick from sample projects. Okay, and this is one of the sample projects. We have object detection, face detection, cats and dogs. Yeah, sure. Maybe. Yeah, fine. I'm all for testing. Cats and dogs. What does it say? It says bottle, sir. Yeah. Yay, deep learning. Yeah, well, that's the thing. It has only 20 things to pick from. So, you know, it's unlikely it's going to say sheep, right? But you never know, right? If I filmed any of you and it said sheep, I'd be embarrassed. So we can do activity detection, etc. So you can, I'll just show you the console afterwards. But you can just select one of those sample projects and deploy them in minutes, OK? But of course, what you want to do is to train your own models. Okay, you want to build your own project. And actually, we gave away a few hundred of those at reInvent, and we ran a hackathon, and people came up with pretty funny stuff. So that's the idea, really, to let people train and build fun apps. So let me show you a quick example here. OK, so yeah, let's look at the Lambda function, for example. OK, so this is the Lambda console. And so this is the actual code that's running on the camera for this model. So basically, we have a function that's going to run forever. OK, as soon as the function starts up, it's going to do this. So it knows about 20 different types of objects. See, so buses and cars and OK. things that are not necessarily easy to fit in a conference room, but still. And then we're just going to grab a frame. Okay, here. Okay, so we're going to grab a frame from the camera. We're going to resize it to whatever input size the model needs. I think it's 300, 300. We're going to run inference. And using the predictions, then we use OpenCV to draw bounding boxes, etc., etc. Okay, so there's actually a bit of magic happening here because we're not running MXNet per se on the camera. We're running a tool called the Intel Inference Engine. Okay, and the Intel Inference Engine is actually it's a prediction layer that has been super optimized for Intel chips. Okay, so there's a conversion step when you actually download the model to the camera, and this is done automatically on the first call of do inference. So whenever you actually call this on a new model for the first time, it's going to be optimized within a few seconds to that Intel format, and this is what is running on the camera. So it's fusing some layers, and it's, again, applying some hardware optimization just for extra performance, basically. Okay, but now it's all taken care of. I mean, you don't have to worry so much about that. Okay, so this is the under the hood look. And yeah, we use OpenCV, and just for fun, we can publish, we can push an IoT message back to the AWS cloud saying, okay, this is what I found. And you could store this in any kind of backend to do analytics and reporting and whatnot. Okay. And yeah, so really quick, this is the DeepLens console, so you can see the sample projects here. Okay. And if you want to create a new project, you would just do this. So basically, a project is a model and a function. So I could pick from one of the existing models, or I could just go and, again, grab one of the models that I train in SageMaker, or I could take a model living in S3, and that would be it. Okay. So again, no disruption between training and prediction. Just train, grab the model, deploy it. Okay. And of course, you would just add your Lambda function as well, and that's pretty much it. Okay, so it's not too complicated. We have a bunch of blog posts on how to do this in detail. So ping me if you need more information. Okay, so yep, we saw all of that. Okay, so yeah, that's another example, playing with my kids. Same, I think it's the same model, actually. It's the object detection model, too. So it worked pretty well. And you can see the chair and the sofa. And my laptop actually says TV monitor, which I guess is close enough. Pretty good. Okay, resources. And yeah, try this with your cat, and you'll pay for this. See my scratches? Anyway, so some resources to dive deeper on all of this. Of course, the MXNet and gluon web pages. I have to say, this specific gluon URL obviously has the gluon docs, but it has a lot of generic information on what deep learning is, how it works, etc., etc. So it's actually a very good resource to learn about deep learning. It was written by one of my colleagues, and he did a really good job at this. If you want to play with SageMaker, we have a free tier available, so you can do that. If you need more information on SageMaker, and we had the San Francisco Summit actually yesterday, and we announced even more things on SageMaker. We open sourced part of the platform, etc., etc. But if you want an overview on what it is, how it works, how you can leverage it to train and deploy your models at scale without managing a single server, I recorded a YouTube video that seems to be quite popular, so maybe you'll like it as well. If you're curious how SageMaker works, we also have we have an SDK and samples on GitHub to show you how you would do, let's say, distributed training with TensorFlow, or how you could bring your R a model to SageMaker, etc., etc. Greengrass, again, there's a free tier for it if you want to try it. DeepLens, so you can't buy the device now. You have to pre-order it from Amazon.com. It should ship mid-June, crossing fingers. If you're curious about that Intel inference engine and what Intel does to optimize inference, this is the link to go to. And last but not least, I guess, my blog on Medium, where I tend to post all kinds of things on machine learning, deep learning, SageMaker, etc., etc. So if you're into those things, then you might enjoy my blog. Okay? And don't do this to your cat. Come on, don't be mean. It said dog for 10 minutes until it said cat. So that's why the dog. Yeah, that's why it's pissed off. Anyway, thank you so much. Thank you, Louis, for inviting me. And if you have questions, I'm happy to take questions.
Yeah, same thing as before. Before taking questions, I'd like to invite up the startups who are about to pitch, just to make sure that everything's set up in time, because we're running a little bit late. But that doesn't mean we can't take questions. Does anyone have any questions for Julien? Yeah. Oh, yes.
Yeah. This is the one you need.
Thank you.
Hi, great presentation. I have a question about the pre-processing of the images, like channel manipulation or a bunch of things that would improve the model performance. But then, does the pre-processing happen on the device, or does it happen like?
So the only thing that happens on the device is I would say the conversion, the model conversion from vanilla MXNet form to Intel optimized form, and then of course prediction. Okay, but the model that we deploy there, it's just a normal model. It's a model that we train in, and our customers train on SageMaker. You could train it elsewhere if you wanted, and of course it has nothing specific. Okay, so you can take your vanilla CNN, your vanilla image dataset, train it, test it in the cloud, and then deploy it to DeepLens. So I would say all the traditional steps that you could take during training to make the model more efficient, I don't know, data augmentation and those different things, they will still apply, of course. Okay, but this really happens during training and, well, before training actually, before data processing, etc. Yeah.
Before being fed in the model. So
yeah.
That pre-processing, I was wondering.
Yeah, you could do. So here, I guess, yeah, we do an extra step, which is resizing. So if you wanted to resize, if you wanted to do, white balance or any kind of normalization, yeah, you could do that in the Lambda function too, right? But keep in mind, this is an Intel atom, right? So don't go wild on pre-processing, otherwise your performance drops, okay? But yeah, totally, resizing, normalization, you could absolutely do that, sure. Thanks.
Hi.
Yep.
I have a question that is more related to MXNet. You mentioned the importance to be optimized for specific hardware and Intel. I'm not using mostly hardware Intel to train deep learning algorithm, but more like NVIDIA hardware. And I was just wondering, the order of the tensor in MXNet, is it like NWHC or NCWH? Because it has it explains some difference between PyTorch and TensorFlow, making PyTorch more efficient on NVIDIA hardware for that. So I'm wondering for MXNet.
Yeah, you control that during training. I mean, if you want to put your, channels, number of channels before height and width.
Yeah, but if I have to do a lot of transposition, it's slow down.
Yeah, I would say what I usually see is, batch size, number of channels, height and width. That's what people tend to use most. But yeah, but if you want to try something else, fine. I would say here, anyway, we're predicting image by image, so it's batch size is 1 all the time. I didn't try predicting more than that. I'm a bit afraid of the performance. It would work, but I guess it would just be choppy, right? And we're trying to get to the highest FPS possible. So probably predicting one at a time is the best thing.